Okay, so I just wrote the definition for you at the top. So we're going to add, subtract, maybe multiply a couple of these questions, see if we can simplify them at all. So it says you can add or subtract what we call like radicals. And then it says like radicals mean the radicals have exactly the same thing underneath. So like, we'll get into this in these next questions, but the radical has to be like, they both have to be square roots or they both have to be cube roots, and they have to have an identical thing underneath, and then you can add them together. So we're just going to look at example 1, and this is just going to be really quick. All right, so I have 7 times the square root of xy and 3 times the square root of xy. See how it says square root of xy? Those are identical. All right, literally all you do is just take the two numbers. I have 7 here, 3 here, so you have 10 square roots of x times y. That's all you have to do. If you look at the next question, I have 2 cube roots of x minus 2 cube roots of 5. So if they don't have the same thing under the radical, then that's as simplified as you can get. I can't do anything more there. That's that question. There's nothing more I can do. This guy here, this is a little tricky. So these are both cube roots of 9. I have 8 here minus, it doesn't have a number in front, but I have a cube root of 9 there. This would just be like 8 minus 1. So this would be 7 cube roots of 9. The radical, the index doesn't change, and what's under the square root does not change if you are adding or subtracting. So this one says 6 cube roots of 7 plus a cube root of 7. So it would be 7 cube roots of 7. What's under the radical should not change if you are adding or subtracting. All right. Somebody raise your hand and tell me, would you be able to subtract e, and what would it be? So I have 7 fourth roots of 5 minus 2 fourth roots of 5. What would I write as my answer? What do you think? Yep. 5 fourth roots of 5. That's all I can do. Can I add 2 roots of 7 and 5 roots of 17? Not the same. Now, you should check if you could break down the radical. Both of those guys are prime. You're not doing any kind of a factor tree that's going to do anything here. So that's as simplified as you can do. You can't actually add or subtract. You guys don't need your computers right now. Let's put those away. Thank you, thank you. All right. Now, what if I have 4 cube roots of 5 minus 10 square roots of 5? Would I simplify that? You can't. Okay, this guy's a cube root, this guy's a square root. So that's as far as it can go. You can't take it any farther than that. All right, and then I got one more. I've got negative 15 fourth roots of 16 and 6 fourth roots of 81. Now, I know this is really tricky, so I'm just going to lay my lovely little yellow piece of paper here for a second. If you look under your fourth roots, 16 is actually a perfect fourth root. So if I have the fourth root of 16, what is that really equal to? 2. Yeah, okay, if it was a square root, we'd say 4. If it's a fourth root, we're going to say 2. So this first term here actually is really negative 15 times 2. Anything you pull out of a radical, if something's in front, you're going to multiply. So this first term is really just negative 30. Okay, now if you guys are looking at my fourth roots again, the fourth root of 81, 81 is a perfect fourth root. What would I get if I took the fourth root of 81? 3. Okay, so really this is actually a plain number too. I already had a 6 out in front, so it'd be 6 times 3. So this is really negative 30 plus 18. So I can't actually add these together because they both end up just being plain numbers. This should end up being negative 12. So if you can break down the radical, you want to try to do that, and that's what we're going to do in the next couple of steps here. They're not necessarily going to be perfect, but they're going to be something that we can break down. Okay, so I tried to mix together square roots, cube roots together in this example, but initially when you look at this, they have all different things in this first example under the square root, but we want to see if we can break them down. So if we like the factor tree, so for 20, maybe I do, let's do like 2 and 10, and then 2 and 5, right? I just need a pair. So I broke down the 20, I broke down the 10. I have a pair of 2s. If you already have a 3 out in front, what do I do with the 3 and the 2? Multiply. Okay, so if you pull a number out in front, just multiply. So 3 times 2 would be 6. So that first term is really 6 square roots of 5. Now, 45, maybe like 9 and 5, and 9 would be 3 and 3. So I broke the 45, I broke the 9. This just has a subtraction sign between these two terms. That second one didn't have anything in front, but when I simplify it, it's going to have a 3 in front of it. So really that second term is minus 3 roots of 5. And then the 80, I'm not going to break this down how most people would, but 80 is the same thing as 16 times 5. And so that's just going to give you 4 and 4. So I can get a pair there. Now, I already have a 4 out in front, so when I remove that 4, it's going to become 16, and then I'd have a 5 underneath. So initially when I looked at that problem, they were not like radicals when I was looking at it, but if I actually take and go through and do our breakdown and put them in simplest radical form, all 3 of these are like radicals. They all have a radical 5. So all you have to do to simplify is literally just take those numbers. So it would be like 6 minus 3 plus 16, and then the square root of 5 would be following that. It's not going to change. So it should be 19 roots of 5. Does anybody have a question? Okay. Now, if I look at this one, these are all cube roots. So remember, when you break these down, you want to take out a group of 3. So there's nothing you're breaking 2 down with. So I'm just going to leave that first one alone. 16. I'm just going to do right from the jump. Let me do 4 and 4. And we'd have 2 and 2, 2 and 2. Now, this is really tricky when we start mixing these together, but I need a group of 3. So I have 3 2s, but I have this extra 2 that's going to have to stay under the cube root here. So it's not a perfect cube. I'm going to pull a 2 out, and I already had a 7 there. So 2 times 7, 14 cube roots of 2. Or tell you what, I'm just going to bring down that first term. Now, the third term, you're not doing anything with the 3. So plus 3 cube roots of 3. The last one, I've got a 54. So I'd probably do, let's see, 9 and 6, 3 and 3, 3 and 2. I'm looking for a group of 3. I have broken the 9, broken the 6, broken the 54. I have 3 3s, but I have a 2 that's not got anybody to hang out with, so it's going to have to stay underneath. We already have a 9 in front here, so when I pull the 3 out, it's going to be minus 27. And then left under the cube root, I have a 2. And this is kind of a weird problem, and I feel like there's one like this on the test and the quiz. So if I'm looking for like radicals, 3 of these have a cube root of 2. So I can combine 3 of those, but this right here is just going to be a separate term. So I'm just going to take the cube roots of 2. So I've got negative 4, then I got 14, so that would be 10, and then minus 27, so I'd have negative 17 cube roots of 2, and then that cube root of 3, we just can't combine it because they're not like, so my answer would have just 2 separate terms here. So it'd be negative 17 cube roots of 2 and 6 cube roots of 3. Okay, I'm going to do one more with you guys because this one's a 4th root, and then I'll have you guys try the last one kind of on your own. So this is a 4th, so I have to have a group of 4 if I take these out. So for 32, I would probably do 2 and 16, and then I don't know, I'll just do 4 and 4 for the 16. All right, I'm looking for a group of 4. This is not a perfect 4th. If I broke the 32, the 16, those 2 4s, I do have a group of 4 2s, but then you do have this 1 that doesn't fit into that group of 4, so it'll be a 2 left underneath. 10 already in front, so I'm going to take a 2 out, so we'd have 20 4th roots of 2. All right. Let's see, 162, sorry, I should have spaced this out a little bit better. 162 is 2 times 81. 81 is 9 times 9. And both of the 9s can go to 3 and 3. So I'm looking for a group of 4. I broke the 162, the 81, and the 2 9s. So I do have a group of 3. or group of four threes, sorry. And again, this has a 2 stuck underneath. If you have that 6 out in front, 6 times 3, their subtraction between these is going to be 18 4th roots of 2. Yikes, and then I got 512. This is a 4th root. Let me divide that by 2. Or you guys can figure out other, I'm just going to do 2 and 256. Now, 256 is going to be 16 and 16. And then I'm going to go 4, 4, 4, 4. So, 256 is going to end up giving me a group right there. And don't keep going. Like if you have a group of 4, don't keep going like 2, 2, 2, 2. That just makes it harder. If you have a group of 4, just stop. So I have a group of 4 4s. Now we broke the 512, the 216 or 256, and then the 2 different 16s there. So again, this one had like an extra 2 that's going to stay underneath. So 3 times 4 out in front is going to be 12 4th roots of 2. So I know that's a little bit of work, but they do actually then end up all being like radicals. So all you have to do, these are all 4th roots of 2. You have 20 minus 18, so that would be 2, and then plus 12. Don't change what's under the radical after you simplify it. Should be 14 4th roots of 2. Okay, you guys try this last one here. Try this last one. I'll give you this. Should get negative 71 cube roots of 3. Now, I learned how to do this a different way. I'm not a factor tree person, so I'm just going to show you what I did real quick. On these second two, I had like 192 and 375. The way I do a breakdown of a radical, just if you're interested, if this would save you any time, what I do is I start looking on the list of perfect cubes. And I try to find a number that would divide into like 192. So if you divide, there's not really that many numbers to check. So like if I do 192 divided by 8, that goes in. If I do 192 divided by 27, that does not go in. 192 divided by 64. 125 would be too much. If you can find the biggest number on that list that'll divide into that, that can help you break it down maybe a little bit faster than a factor tree, if that makes any sense. So I just rewrote that as 64 times 3. 3rd root of 64 is 4, so I pulled that out in front. If you like that better than the factor tree, feel free. If I'm doing the 375, again, I'm checking to see what numbers on that list of perfect cubes would go into it. So I just grabbed my calculator, did 375, I checked 125, and it was 125 times 3, so I just rewrote that, and then the cube root of 125 is 5. So if you guys want to try that instead of a factor tree, that might be a little bit faster, but just an option for you. The factor tree obviously works as well. Is anybody having a question? Okay, now these two on the back are just a tiny bit weird. So the first one is a square root. So, and I don't know if you guys will know this, my list doesn't go up this high, but 225 is actually a perfect square. Does anybody know square root of 225? Yes. Okay, so really, I can simplify that right then and there. So 3 times 15, this would be 45, roots of x. I just wrote that really weird, sorry. And then 144, I know you guys know that, square root of that is 12, so I can remove that. So that second term, I have a 5 out in front, just multiply these guys. This is 60 roots of x. So these do end up being like radicals, even though they didn't look like it initially. And so let's see, 45 and 60, this would just be 105. And then again, if you're adding or subtracting radicals, you're not actually changing what is underneath the radical. It should still just be square root of x. All right, now these last two, this is kind of a review of several things. So 45. Now, I'll just show you my way instead of the factor tree. If you like the factor tree, use the factor tree. I'm just going to show you this real quick. So 45 under a square root, I try to think of the biggest number that's a perfect square that'll divide into 45, and that's 9. So I would just rewrite that as 9 times 5 real quick. Y squared is actually a perfect square root in our variable situation because that exponent is divisible by 2, so I'm going to leave that alone for 1 second. and then 20. Again, factor tree if you're into that. If you want to find the biggest perfect square that goes into 20, if you're looking at your list of perfect squares, it is actually 4. So I'm just going to rewrite that as 4 times 5 real quick. If you rather the factor tree, please use the factor tree. If you want to remove perfect squares like I wrote it here, this would come out as 3, this would come out as y, this would come out as 2, this would also come out as y. Anything we remove, we're just going to multiply everybody in front. So 3 times 6 is going to give you 18 times y. So it would be 18y times the square root of 5. And the other one, I'm going to bring out the 2. 4 times 2 is 8. And then the y there, radical 5. And then this is kind of weird, but these are like radicals. So you can add the terms in front, and they are like terms. So 18y and 8y, we're not multiplying anything, we're not changing the exponents. It's literally just 18 plus 8, 26 y's, and no exponent or anything like that, just 26 y's and then radical 5. So just a couple weird ones there. Is anybody having a question? We're going to kind of switch gears and do something a little different. Okay, but it's going to involve, yeah, question? Right, okay, so y squared is, so if I just give you like square root of y squared, the index of the root there is 2. They usually just don't write it on a square root, but you just divide the exponent by the root. So it just would pull a y out in front, just like we were doing earlier in the week. Yeah, it's the same thing. It's just it's a perfect square there. Really good question. Anybody else have a question? Okay, now I'm going to have you guys do some multiplying here, but it's going to also involve adding and subtracting like radicals if possible, which is why I wanted to practice that first. So this is just, these first two questions are just like a little distributive property. You can always multiply. So I'm going to multiply the square root of 7 times both of these terms here. You can always multiply. If you multiply a radical by a plain number, the proper notation there is to just put that plain number out in front so you don't confuse it and maybe think that the 4 is supposed to go under the square root too. So square root of 7 times 4, we would write that as 4 roots of 7. Now, if you multiply like radical, or it doesn't matter if they're like radicals, as long as they're both a square root, you just literally multiply the numbers together. So root 7 times root 7 would actually be square root of 49. And then in that particular case, that's a perfect square, so that would just become 7. And I can't go any further than this because I can't add that 4 roots of 7 to a plain number, but I can simplify that 49 under the square root. All right, you can always multiply as long as they're the same type. These are all square roots. So negative root 8 times the square root of 2 would be negative out in front. 8 times 2, 16 underneath. I'm just going to wait for a second. Negative times a negative would be plus, and then 8 times 10 would be 80. All right, the first term actually ends up being a nice perfect square. It does a negative not underneath, so we can do it. It's negative out in front. This term would just become negative 4. Now with the 80, if you guys are more into the factor tree, I can do the 80 under the factor tree too. I would do 16 times 5, and then you got 4 times 4. So your pair of 4s, so that would simplify to be 4 roots of 5. And then for that problem, you can't go any farther than that. I can't add the plain number negative 4 to 4 roots of 5, so we would just have 2 separate terms. Does anybody have a question? Okay, now the rest of these. You are welcome to do a box. I'm just going to do like a foil, but if you want to draw yourself a 2x2 box, you can do that for any of these questions. But this looks like, this would be kind of like, you know, if we had x plus 5 times x plus 5, it's the same format. We're just multiplying these numbers in like a foil, or I just think of it as a double distributive property. And you can always multiply. You might be able to combine some like terms as we go through here. It's going to depend on the question. So if I do 8 times 1, I'm just going to get 8. 8 times that negative root 11, we would just write that as minus 8 roots of 11. Get a number times a radical, just put the number in front so that way we don't confuse it and think it's underneath. Then I'm going to multiply both of these guys by square root of 11. So square root of 11 times 1 would just be plus square root of 11. If you wanted to put a 1 in front of that, I would never count you off for that or anything like that, but most of the time they wouldn't do that. Now the last term, positive times a negative, so it's going to be a negative. 11 times 11, this is going to create a perfect square under the square root, so we'll be able to simplify that. So I have 8. Now in here, these guys actually end up being like radicals, so we can put them together. You have negative 8 roots of 11 plus 1 root of 11, so it'd be negative 7 roots of 11. And then on the end here, square root of 121 is 11, but it would be subtracted there. The only other thing I can do to simplify this question, I can put the 8 and the negative 11 together. So 8 minus 11, I'm just going to write it out in front, be negative 3 minus 7 roots of 11. Anybody have a question? Yeah. Honestly, it doesn't matter. It doesn't matter. However you want to write it, as long as you have both terms, that's completely fine. Completely fine. Excellent question. Anybody else have a question? Yeah. Say that one more time. Oh, okay. Very good question. All right. So this, like in your order of operations, right? It's attached to this. So, no, and that's something that people want to do. Like, so that's attached. So I would have to do that multiplication first before we could do the subtraction, but I can't do anything there. That's a really good question. Those have to stay two separate terms. So this is a plain number, and that has that radical attached to it. Really good question. All right, now the last one. Don't do this. Don't distribute the exponent, okay? Anytime there's adding or subtracting in here, if you're squaring something, it means you are multiplying it by itself. So you are just going to, bless you. Seriously, my pen is going to die right now. Okay. So, fail. All right, just write it twice. If you're squaring it, if you were doing it 3 times, we would write it 3 times. All right, because if you don't, you're going to completely screw up and miss up the middle term. All right, you can always multiply these together. So, when you multiply, let me do, okay, square root of 2 times square root of 2. Square root of 4. I'm just going to wait for a second to simplify that. Square root of 2 times the negative square root of 3. This would have a subtraction sign. 2 times 3 would be a 6 under the square root. Okay, then I'm going to multiply both of these guys by negative square root of 3. So negative square root of 3 times 2 is negative square root of 6. And then negative times a negative for this last term. Negative times a negative is going to make a plus. And then root 3 times root 3 would be root 9. Now, in this particular case, 2 of these simplify. Like this just becomes 2, and this just becomes 3. Just plain numbers. Now, this is weird. The ones in the middle, though, these don't cancel each other out. You have negative, like a negative 1 square root of 6, negative 1 square root of 6. So together I have negative 2 square roots of 6. Now, the only other thing you can do there, the first couple terms we had square root of 4, square root of 9, which is 2 and 3. Put the 2 and 3 together. You can do that. 2 and 3 is going to be 5, and then minus 2 roots of 6. But you can't go any further than that. You can't actually subtract the 2 from the 5 because that 2 is attached to that square root of 6. Okay, and I'm going to do one more, and this is going to kind of lead a little bit more into what we'll do in our next lesson. But you guys will notice these are almost identical, but one's a plus and one's a minus. All right, so do the same thing, just like a little foil. 5 times 5 is 25. 5 times that negative root 2, we would just write a negative 5 in front of the square root of 2. Then I'm going to take the square root of 2, multiply by both these guys. So square root of 2 times 5 would be plus 5 roots of 2. And then on the end, positive times a negative is always going to make a negative. And I have root 2 times root 2, so it would be minus the square root of 4. Now, here's the deal. These two middle terms, these are like radicals. We can add them together, but they actually cancel each other out because one's a positive 5 and one's a negative 5. So those are both gone. That first term was just 25. This term on the end does end up being a perfect square. So square root of 4 is 2, and that's being subtracted. So it'd be 25 minus 2. So all that work, this actually ends up being just a plain number. That's 23. And like I said, we're going to do some more similar problems to this in our next lesson. Is anybody having a question?